Okay, I think it's 2 o'clock. So, as my title says, I want to talk about materials which are modulated in time as well as. Yeah. What? You can't hear? Oh, excuse me. Okay, is that better? Right, thank you, Eli. Materials which are changing in time as well as space. This has been a subject which has visited on and off over the years, and in the past there's fizzled out largely because there aren't experiments available. But now experiments are becoming available, and there are systems which can change the properties of material on the time scale of one period of irradiation. So we're getting there. Not quite able to do some of the more extreme things I want to talk about today, but we are getting there. Before I go any further, I should mention my collaborators: Emmanuel, who is my student, Paloma, my postdoc, Simon, who is my collaborator, particularly on the quantum aspects I'll talk about today, and Ricardo, who's in our experimental group and has been looking at some of the time-dependent systems. Unfortunately, I won't have time to talk about Ricardo's work today. Right, okay. I did hear that this would move the thing forward, but it doesn't, so, and that won't move it forward either. So this machine seems to have frozen. Your screen share, stop share. My screen share, it's frozen.
What's it? What happened?
Oh, it's not working now. Okay.
Just give it, or you can use this, or you can use.
Yeah, this wasn't working.
It's working.
Oh, there it goes. Yeah. Okay.
Just give me 1 second, please.
Okay, that's fine.
Just let me hide. Yeah, I think you can use these two. This is for backward and this is for forward. Now try. Backward, forward. Yeah.
Okay. Where was I? Yes, materials which depend on time as well as space. Now, the sort of time dependence I'm interested in is a time dependence in where the medium doesn't physically move, but it appears to move. It's virtual move. It is virtual motion. So it's a sort of motion where locally you decide to change that stationary system at a certain point in time to a certain value, and at another point you decide to change to another value at a certain point in time. So this is a sort of wave motion, like in the ocean, where a wave moves across the surface of the ocean, but it isn't what you're seeing. It's not the flow of water; it's the flow of the wave itself. And one of the important consequences of that is that because nothing physically moves, there is no restriction on the velocity of these structures. They can move with any velocity up to infinity. So that's very flexible. But there's another more subtle quality that you see, and it's this: that if a medium physically moves, then there's a Doppler shift associated with the properties. And what then happens is what you see here. So if you have a material which is in linear motion, then this is the analytic structure of the medium. And for a stationary medium, all the poles in the dielectric function or the permeability are in the upper half playing the negative frequencies and the lower half playing the positive frequencies. And that is important because it means that a stationary medium, passive medium, cannot put energy into the system. And it can only give loss. But once you start moving that medium around, you find that these poles are doubly shifted, and that's only with linear motion. So you can imagine if you have a complex motion, what a mess these poles are to consider. So it's a huge theoretical simplification to take these systems which are in apparent motion, virtual motion. One of the first systems we looked at was to ask if this virtual motion can simulate some of the effects that real motion has. And a very old example of the real motion is Fresnel drive. So we asked the question whether a material modulated in space in a time-dependent fashion, and so the material itself remains stationary, whether this medium, as a wave moves through it, can drive light along with it in the manner of the Fresnel drive. So a long time ago, Fresnel asked what would happen to light moving in a medium which was itself moving. Would the medium drag the light along with it? And his answer was yes. And he gave a formula that was correct, but his derivation was wrong. And it turns out that the correct derivation is due to Einstein. And how on earth Fresnel got the right answer, I don't know, but he did. That's Fresnel, for a brilliant man, ahead of his time. And Fresnel drag is one of the foundations of special relativity, it turns out. Years later, Fizeau did this experiment, which I show here, in which you have a fluid flowing, and then you send light two ways through this, and then into an interferometer, and the movement of its fringes tells you about the drag of light, whether the light goes slower in this direction and faster in this direction. And the answer supported Fresnel-Einstein formula. Well, you can do an analytic theory of this, and what comes out is that you have a dispersion relationship which modifies the frequency of the light and the wave vector of the light, but most importantly, there is this alteration of the wave vector in the direction of flow of the liquid, and it's altered by something which is proportional to the frequency here. And that means this delta, when it's finite, means that there's a drag acting on the light. And if you look at the dispersion surfaces, you can see that the circle is the free space one, black circle, and the red circle is the dispersion when you turn on the moving grating. You can see that the grating is indeed dragging along the line in one direction or the other. So yes, these systems which in which you don't have to move the medium itself, it's just a modulation that moves, they are capable of simulating many of the effects, faking many of the effects which come from a real moving medium, but not all of them, of course. It's interesting, I won't go through all this formalism here, but it's interesting to ask what affects this value of the Fresnel drag here. And if you see this expression here, which is in terms of the frequency and wave vector of the grating and the modulation amplitudes of epsilon and mu, what turns out is that you have to modulate both epsilon and mu in order to see this drag. And the explanation of that seems to be that if you have just an electrical polarization, the electrical dipole radiates symmetrically forwards and backwards. And it's only if you have a magnetic component as well as an electrical component that you can get asymmetrical radiation and therefore drag. So a rather curious thing, but it does give us confidence to press ahead. Now, the next thing you can ask is if you have a medium which is in motion,
sorry, medium is in motion, but you have a disturbance in the medium which moves, then it brings tangular symmetry, but it's actually parity down symmetric. So this is the simplest moving structure to imagine. It's a bright grating, but it's one which drifts along in time. And I'm going to be particularly interested in the case where that grating is moving almost at the speed of light, what I call the transluminal region. And then you find that the epsilon and the mu's can be established in this form here. And what you notice, and I'll come back to that later, is that you have this singularity here. So omega divided by g is the velocity of the grating. So when the grating velocity is equal to the velocity of light in the medium, these guys are singular. And I'll return to that when I come to talk about Hawking radiation.
Now, this slide sums up most of the things I'll talk about today.
So here's a grating. It's moving in this direction here. And where epsilon is large, the light moves more slowly. And where epsilon is small, it moves more quickly. Of course, the refractive index changes in that way. And if there's a point in the grating where the velocity of the grating is the same as the velocity of light at that point, then something interesting happens. In the meantime, I should point out that in this red section here, as the grating moves along, the local value of epsilon is decreasing in time. And under those conditions, you're actually pumping energy into the system. So this section is sort of hot, it's creating energy. And what's more, this energy doesn't stay still, because any photons created here, any energy created here, will be faster than the grating until it will move to this point. Here, it's going slower than the grating, so it moves to this point here. So here is an accumulation point where you get compression of the radiation. And to give you an idea of what comes out of the grating, so you put in a uniform plane wave, you show it in the grating, and here are the periods of grating, excuse me, and the pulse gets compressed into the accumulation points, which are shown here. I also show these grey lines, which are indicating the strength of the lines of force associated with the radiation. And you can show that the lines of force are conserved and they're merely compressed. And if you compress lines of force, just as you put a magnet over a superconductor and press the lines of force, you get repulsion, you put energy into the system. Same thing happens with the phase is compressed. So it's as if the whole wave is just taken as it is and squeezed into this pulse. And as the as you increase the length of the grating here, this compression just goes on and eventually is cut off by limitations in the physical properties of the material. Now, you can show that the form of the pulse compression is compression phase by a factor F, and the compression of the lines of flux mirrors is F prime, so they compress in the same way. And here's an expression for F. And if you work through this analytic theory, you can ask for the distribution of energy. So if you compress radiation, of course, you're putting energy into it, so you can ask, what is the frequency spectrum of that energy? And it turns out it's like black body radiation. So the distribution frequency follows a law like this, with a temperature called TH, which is given in terms of the grating parameter, H bar, and the amplitude of modulation, and the length of the grating, and the reciprocal lattice vector of the grating. So there's a temperature shown with it, and the compressed pulses get hot. And again, I'll come to the back and show that that is a mirror of Hawking radiation.
Now, when we look at systems, we almost always look for conservation laws. So fundamental to our understanding of the universe are conserved quantities like mass, energy, charge, spin. And these are the tools with which we forge our understanding of the world around us. So one should always look for conservation laws. Now, in this system, you lose the conservation of energy, obviously, because you're doing work on the system and you're compressing these pulses, as I've shown, and the pulses get hot. But there is another conservation law, and it's conservation of photons. So what happens in this process is that the photons in are equal to the photons out. So if you conserve photons, and there's a recent paper in which so how do you put energy into the system? Well, you start with a finite number of photons, and the only way you can put energy into the system is to have them climb this ladder of frequencies here. And as they do so, they get hot, of course. So that is the way that energy is entered into the system. Now, I won't go into great detail about photon number conservation, but you can show from Maxwell's equations that there is a conservation law for photons. And what you can show is that if you make an expansion of, so here are the modes, excuse me, yes, what was the next slide? Yeah. Okay, so I have two fields here, and I'm expanding the fields as a sum of the modes. So each mode, the nth mode, is composed of these Fourier components here, summed over these n Fourier components. And when I want to know the flux of photons, I take the Poynting vector and I divide it by the energy of the photons. And then I sum over all the components in that mode, and then I sum over all the modes, and of course the modes overlap. Now it turns out that if you integrate sum over all these modes are orthogonal. And so this is only non-zero if L is equal to L prime, and so you sum up and find that this number here is conserved if it's conserved in these individual modes. Now, what I want to point out to you is that the orthogonality condition is not between these components of Poynting vector. It's these divided by the frequency. And that doesn't matter if the frequency is constant, of course, but the frequency isn't constant. And that's why you have photon number conservation, which of course, if the frequency is constant, is associated with energy conservation. But in this system, you keep photon conservation, but you lose energy conservation. And you can do a few simulations of how the photon occupancy change. So we start with a plane wave, and we turn on this grating I mentioned before, and then the grating scatters the plane wave into higher frequency components, and we plot the photon count at each frequency. So we divide d squared by the photon frequency. And you can see here, here's the calculation of the photon count for a short grating, 32 periods, and a long grating for 64 periods. And you can see what the grating is doing. It's shoving these photons out, they're climbing the ladder, and more high energy states are populated, the stuff gets hot. Just for interest, I plot down here the energy occupation of these states, and that climbs simply because the photon energy is increasing. So that we understand quite well. But I wasn't quite straightforward with you when I gave you that expression for photon conservation, because this is the expression which is true when you divide the Poynting vector by omega plus n omega. You find that
this pseudo photon number is conserved. That's what's rigorously conserved. But that isn't the true photon number, because negative frequency photons have positive energy. We can't get around that. You can't, even if I gave you a photon with a negative frequency, your counter or whatever would say, ah, yes, that's a positive energy. So you have to adopt this formula here. Now, that causes some interesting situations, because there is no problem if you're only making transitions between positive frequencies, because then the issue of the sign of the omega does not arise. But if you, and similarly, if you're making transitions between negative frequencies, because although you have a negative sign here, it's still conserved, the number there. And when you get a problem, it's when you have some frequencies which are positive and some frequencies are negative. And that's perfectly possible in this grating, because it's making transitions up and down the ladder and crossing that plus minus barrier. And this has quantum implications. So when there's a mixture of positive and negative frequencies, you do not have photon number conservation. So let's suppose that we start off with a number of photons n0, but some of these photons transition to negative frequencies. So the pseudo number is conserved, so that's always at 0, because we proved that. And the actual number is n minus n0, which is the actual number. That's the number you start off with, and that's n minus n tilde. And now tilde, this differs from n in that we've taken one of the positive frequency photons, which counts with +1, and you've subtracted 1, and then you've added it to a negative frequency, which counts as -1. So when we do the sums to calculate n, we've actually changed the photon number by 2. So non-conservation implies that for every crossing of the 0 frequency, there's a creation or annihilation of a qubit of the photon n. So how many photons are created in this grating? Well, if you plot the probability of photon pair creation versus log of the length of the grating, you can see that it grows very rapidly, and then it saturates at some point here. And what's happening here is that you start off with some frequencies which are near 0, and most of them head off to very high positive frequencies. Those which cross the boundary head off to very high negative frequencies, and so the region near the origin is depopulated, and that accounts for this saturation. Yeah. So, what is Hawking radiation? So, Hawking showed that if you look at the Schwarzschild metric in the presence of a black hole, then the metric has this form here as a function of the radius. Now, as far as light is concerned, the metric is a refractive index for light. And it's a situation where you have a p matching in our language, and essentially everything equals mu. And this Schwarzschild singularity, when the refractive index goes to infinity, occurs this Schwarzschild radius, which occurs if the mass is great enough, and so that can happen outside the physical mass of the black hole. Now, I did point out to you earlier, I'm not sure if I go it again here, that our grating, when the velocity of the grating is the same as the velocity of light at some point within the grating, that also has a singularity. And this singularity is of the same order as the Hawking singularity, which we show here. It's a pole. And therefore, we ask the question, essentially Simon Horsley and myself, of whether you can get spontaneous emission in this circumstance here. And the answer is yes. So what you can do is to calculate the quantum form of the Maxwell's equations. Here's a Hamiltonian, and here are the traditional operators of a harmonic oscillator, which is the electromagnetic field. And you can see this is the term which we normally see, which measures the number of photons in each state. And this term here conserves photons, of course. So everyone you annihilate, you create one. For everyone you create, you annihilate one. And so that conserves photons. But these terms here, when n and n prime correspond to frequencies of the opposite sign, these flip their attributions, and you get a pair of creation operators and a pair of annihilation operators. So this is a term which actually is going to give us a Hawking radiation. And if you read Hawking's paper, he makes the point that considering of negative frequencies is essential to the creation of his Hawking radiation. So you can calculate out what that does. And what you find is that, Simon disagrees with me on this. He calls this a black hole and this is a white hole. But anyway, black hole white, this singularity here will not only take incident radiation and compress it, it will grab quantum fluctuations from the background, and providing the transition from a negative frequency to a positive frequency or vice versa, it will act as though they're real hot photons, and it will compress them and make radiation. So if you can make a grating moving like this, then you will see radiation from it. And the amount of radiation is not trivial. But the difficulty is making a system like that. But we have a solution. So yes, instability. When you look at radiation from atoms, you can have spontaneous emission of that radiation. But Einstein showed, and this is the basis of the laser, which you all know very well, is that you can have stimulated emission. So a passing photon can persuade that atom to give up its photon to that quantum state. And just as you can have stimulated emission of radiation from atoms, so you can have stimulated emission of radiation from a Hawking singularity. And of course, because you can make the stimulation as almost as strong as you want, the stimulated emission can be much greater than the Hawking radiation was itself. And this is quite important if you want to use systems of low frequency, where the photons have very little energy, but where the low frequency means that you have a chance of modulating the system as quickly as you need to do to see this effect. But the question is that the only frequencies which have been stimulated are those with negative frequencies. So if you see radiation with a negative frequency, then that has been stimulated by a Hawking process. But I've just told you the negative frequencies have positive energies. So how do we know that they're negative? Well, there's an answer to that. So there's this problem that if you have a negative frequency, it still shows up with a positive energy. But what we have here is that the frequency doesn't change continuously. It changes in this grating in multiples of big omega here. So if we look at positive energies, modulo omega, we will always have this here. But if we look at negative frequencies, providing that the simulated frequency is not a multiple of half omega, then the modulus of this will be different from the modulus of that when these frequencies change in sign. So by looking at the frequency, you can tell whether somebody has made a transition. So it's possible using acoustics to see stimulated Hawking radiation, whether you pass the zero threshold or not. And so I think I'm on time. Delay is not considered. Let me summarize. So we're interested in gratings which move, which appear to move at near the speed of light, the transluminal region. These can compress radiation to a series of pulses, one per period of rating. These pulses are hot, and you can calculate their temperature in terms of relative parameters. Quantum processes take place during amplification. Promotion of photons to positive frequencies conserves photon numbers. And when you get a transition to a negative frequency, that happens by creation of qubits. So a photon itself never goes to a negative frequency. It merely acquires another partner and then a matching partner at negative frequencies. And the number of photons created in each period saturates the function of time for which the grating exists. I have to say that although this is for a very specific model, a moving grating, Bragg grating, the conclusions hold for a variety of structures. And with that, I thank you for your attention.